We're going to keep rolling on. One more speaker in the clinical outcomes panel before lunch, and then there'll be an opportunity to have discussion around these issues in the panel. And so this is our chance to hear about sensor technologies from Sandy Eckel, who's an assistant professor in the Division of Biostatistics at the University of Southern California. Thank you.
Thank you. So I'm delighted to join you here today, and I'm excited that our morning session has actually been bookended by statisticians. So hopefully that's been good for you. It's been good for me. And so to start off, I wanted to just acknowledge that, of course, I am part of a very multidisciplinary team, so I wanted to acknowledge everyone that I've been working with, and the work that I'll be talking about today has been funded by the NIBIB. So let's see. How do I move this forward? Oh, I see. The big green arrow. Okay, so the work that I'll be talking about today is really motivated by the problem of asthma management. Asthma is a huge public health problem. I mentioned I'm a statistician. I'm also a statistic. I'm one of these 25 million people who have asthma. You know, we know that many people with asthma have asthma attacks, and these cause great burden to society in terms of the costs and lost productivity. However, it's known that many asthma attacks can be prevented if asthma patients are appropriately taking their long-term controller medicine, which is challenging because if you're feeling pretty good, it's hard to remember to take medicines, and if you're also avoiding your asthma triggers. So this really was the motivation for what's called the PRISMS project, and this project was launched in 2015 by the NIBIB, and this PRISMS stands for the Pediatric Research Using Integrated Sensor Monitoring Systems. And the goal of this project was really to develop a tool, a sensor-based integrated health monitoring system for measuring environmental, physiological, and behavioral factors in pediatric epidemiology studies of asthma, with the goal that this tool could then be extended to other types of chronic diseases. So the way that this project was really set up was having 3 different arms. And so there are actually 6 different sensor development groups across the US and 2 bioinformatics platforms. One of them is at UCLA, USC, so I'm part of that. And then there's also a data coordinating center at USC, and I'm part of that as well. And so this is the general idea for the PRISMS sort of ecosystem, if you will. You can see that patients will interact with PRISMS through smartwatches or smartphones. And then these smartphones will upload data securely to the informatics platform and then as well to the data coordinating center. And then data will be linked, this individual level data will be linked to external environmental data, for example, from EPA monitoring networks or pollen count data. And then we'll also be incorporating electronic health record data as well. Then we will integrate and synchronize the data, summarize it, do predictive modeling. So this is where the statistical part comes in especially. And then potentially there'll be even feedback back to patients. I think this will really be key in getting patient engagement and patient compliance with the PRISMS approach. And there might be information fed back to healthcare providers as well. And then the cycle continues. So in terms of the types of data to be collected, I'll focus mainly on the sensor data because that's what's unique about this talk. Let's see. So in terms of the sensor data, we're having children wear smart watches because they tend to wear these a little bit better than smartphones, which are harder to carry around, but we do want the smartphones relatively nearby. But most of these smart watches in general have GPS and accelerometers and gyroscopes to help predict activities, which will be important in trying to understand their microenvironments as well as whether they could be at increased risk of asthma due to exercise, for example. We'll also have children be carrying around portable spirometers that are Bluetooth enabled. This is an example of a sensor that's more of an on-demand type sensor rather than something that is continuously gathering data. We'll also be using smart inhalers, so-called smart inhalers. And so basically what these do is they GPS and time stamp the use of a rescue inhaler or a controller medication. And then there also will be sensors that measure things like air pollution, actually getting personal measurements of air pollution. And so one of the common sort of features of this type of data is that sensor data typically have a timestamp. Not all sensor data have a GPS stamp, but many of them do. And usually they are recording multiple or single features, and the level of pre-processing of this data really varies across sensors. And then another feature to keep in mind is that Many sensors record at very high frequencies data, for example, 50 hertz recording of data, but the upload frequency can really vary, and it's really optimized to conserve battery power. And then we'll also be gathering real-time environmental data, for example, from air quality networks and so on. And another really key portion of this study is to be collecting data through EMA, ecological momentary assessment. And the idea of this is that the day is broken up into time chunks, for example, 2 hours, and randomly timed questionnaires are given during these intervals to assess context, behavior, stress levels, and so on that could be related to health outcomes, and then as well as asthma control test type questions as well. And some of these EMA assessments are also going to be context sensitive triggered. So for example, if you used your inhaler, you'll get a questionnaire that will ask, what caused you to use that inhaler? Was it a preemptive use because you were going to go exercise, or were you actually having an asthma attack? And then also we're going to be trying to include electronic health record data as well as in the previous lecture. So to give you an example of what this data looks like, I'm coming from more of a traditional environmental statistician kind of perspective, where I've come from working on cohort studies that we would collect data annually in questionnaire and sort of spirometry type settings. And this type of data is totally different. As I mentioned, it comes in at a very high velocity, one of these big data keywords. And you can see this is an example from an initial pilot study during an evening commute where a participant, one of our field team members, was wearing a number of sensors. And so you can see that the smartphone was giving information on geolocation, not only the GPS coordinates, but also on the accuracy of that GPS signal. Also, there was physiological sensors, so they were wearing a heart monitor around their chest, so we have heart rate and breathing rate from that. And then there's also meteorology sensors, talking about temperature and relative humidity. And so you can just get a sense of how this is over just a 2-hour period, how dense that data is. Similarly, from this same study, we can look at the GPS trajectory and link this to the measured exposure from that personal monitor, and we can also link it to these continuous measurements of a health outcome, the heart rate. And so you can see, I don't want to read too much into this because it's just one example, but you can see that pollution was higher here in LA, and then as this person drove home to their beach community where they lived, pollution levels went down, and also you can see that the heart rate was a little bit higher close to work, and then as they're getting home, it seems to decline as well. At this stage, we're really trying to get a handle of this data. I feel like wearables is such a new field. So at this point, we've been conceptualizing of what are the major data challenges that we'll be facing. And so I'm just going to give you an overview of some of these challenges, some of the themes that we've been trying to think about, and then I'll talk about just an initial operationalization of these issues. In our group, we have these sensor development teams and also the platform developers. And so one of their major tasks is to evaluate the sensors in terms of reliability, validity, and so on. And then the informatics platforms are also launching some data collection. And actually, as of today is the first day that the UCLA USC group is collecting data in pediatric patients. And so these activities will provide really important metadata that will be important to inform the analyses. Thinking about more traditional data analysis paradigms, we're used to thinking about issues of measurement error and missing data, but I think there's an open question for how to incorporate this type of data into the more machine learning type machinery that's used in big data problems. So here are sort of my key themes. I think that one of the first steps that we'll be doing a lot is this idea of doing unsupervised learning, trying to cluster patients together based on baseline data or electronic health records. And I'll have to look into your algorithms because I'm very curious to learn about these, Marilyn. As well as a really key feature that we've started to understand is that the data that's going to come in is going to be so rich that we're going to be able to build pretty individualized models very early on. And so to really understand what someone's baseline levels are of their health outcomes or their exposures, and then start to identify what the deviations are from these. So one of the first steps will be identifying individual level baselines, and then building supervised prediction models really to target deviations from those baselines. And as we conceptualized it, we thought that we'd be increasingly personalizing models, with initial models being really population-based, more similar to the types of epi studies that we're used to, and then really building a model specific to you. And these models can be, a series of models like I've listed here, or we could even think about combining these models in an ensemble learning type approach. And I think that for some health outcomes like heart rate, we might be able to build very individualized models, but if it's a health outcome that's relatively rare, like hospitalization for asthma, we'll have to borrow more strength across people in order to be able to model that effectively. And then another thing to think about, since we do have this real-time streaming data, how often are we going to update our model? And so right now we've been thinking about using a real-time prediction paradigm where we would train the model offline. For example, we might retrain it every night, and then we can give sort of real-time predictions by taking that trained model and then being able to potentially to inform the patient in a relatively short time frame about whether their risk for exacerbation has increased. So this is now my slide talking about the operationalization of some of these key ideas. We have had some pilot study coming through, and so this is how we've been trying to operationalize it, really focusing on the sensors. So we start off with raw data files, and then one of the key things that we realized early on is that we need to think carefully about filtering these very noisy data. So we're using things like median filters, Butterworth filters, trying to get rid of some of the extra noise. And then another thing that is very operational is just how do we align these data? Sensors measure by their nature at different frequencies, and then even sensors that might measure at the same frequency, they might have slightly different timestamps. So how are we going to interpolate and align that data so that we can then integrate it? And then we've also been looking a lot into the field of activity prediction from accelerometer and gyroscope, because I believe this is one of the most well-developed areas in wearable technologies. And so just to give you a flavor of some of the feature engineering that goes on, in accelerometer and gyroscope, we have 6 data streams from 2 triaxial sensors. And these 6 data streams are transformed usually into 17 or so different data streams. They take derivatives, they take Euclidean norms. There's all these transformations that go on. And then there is a windowing approach that happens where you take some sort of statistical summary of the data within, for example, a 1-minute window or so on. And so it's very common in these problems to take 6 data streams and transform it into 500 plus variables that go into our prediction models. So it's really quite a feat. And then the next steps, of course, will be some sort of modeling approach, be it machine learning or more traditional methods, and then interpreting our models. So I wanted to touch briefly on 2 more detailed issues. And so I think that one of the major challenges for these types of sensor data linking the exposures to the health outcomes is that exposures are measured at a much higher time resolution generally than the health outcomes will be. It is the exception rather than the rule that a health outcome might be measured continuously, something like heart rate, but the outcomes that we might be more interested in are typically measured either at regular intervals or intermittently. And so as you can see in this diagram here, you can think about the fact that we're measuring exposure continuously, and we have these intermittent outcomes, and then we need to somehow summarize a history of exposure and relate it to that outcome. Another key thing, I think, discussing GIS information and how do we link these GPS trajectories to exposure surfaces. There was a very nice talk a week or so ago at the NIHS Exposome webinar, and it was discussed the idea of time-weighted kernel density smooth. So rather than using just a circular buffer, actually having a distance decay and a time weighting to more accurately assign exposures, I think will be very important. And so sort of addressing the questions that were asked to us as speakers, what questions can we answer with these sorts of sensor data? So I can really see these sensor data both impacting environmental epidemiology and precision medicine. I think it really is a new paradigm for exposure science. And I think it will help us this highly time-resolved data will really help us to better understand the time response of exposure and health response. And it will help us give better context to measurements of exposure. We know that particulate matter has health effects, but particulate matter comes from many different sources, and we don't really understand, for example, is PM from cooking less harmful than PM from traffic? And so these sorts of technologies will help us answer those questions. We might also identify new sources or triggers using, for example, GPS data or time-resolved data. We might actually identify sort of proxies for other exposures. And by digging more deeply into the data, we might be able to identify those unknown sources. We can also get a better understanding of the heterogeneity of response to exposure, because rather than building these population-level models, we'll be building individual-level models so we can better understand how each person responds. And then finally, can personalized data improve asthma management? I think this is really key in terms of patient empowerment and engagement. And I just want to give two brief examples because I think this is an open field and there have been not that many proofs of principle. So I'm going to give you two brief examples here. One is a very personal example. So as I got involved in this field of wearable sensors, I happened to buy myself a smart scale right around the time that I found out I was pregnant with my first and only child. And so I was measuring my weight approximately daily. And so over this period, I was able to look at my weight gain during the first trimester, and actually it was kind of flat because I had some nausea and food aversions. And then I was able to look at my weight gain over the second and third trimesters. And since I was a statistician, I really wanted to quantify, was I within that recommended 1 pound per week weight gain or not? And I was for the second semester. The third trimester, I was a little bit higher than that. But as a sort of a patient going to my doctor during that time, I found it actually pretty empowering to know what my weight gain was, because in the clinic, they base their assessment of weight gain on these very noisy measurements, once a week. You might be wearing different clothes, you might be in a different digestive status, and so the information that they have there to give guidance on what your current weight gain status is very noisy, and so I found this to be personally very empowering. And then back really on the subject of sort of asthma and environmental health, this was a good example that I came across the other day that I feel like is a very PRISMS-like study, and so in this study. They had personal measurements of exposure, and they divided these measurements of exposure into the various microenvironments. And they used this sort of novel idea of taking various summaries within these microenvironments. So rather than looking at the average of the exposure within each microenvironment, they actually looked at spikes of exposure. And they found that the spikes of exposure during the transit time had a stronger association with the urinary biomarker of exposure than did spikes during the at-home or at-school time period. And so my final slide here, what are the challenges and open questions? Wearable sensors have to be worn. There are major issues with compliance. I think an open question is, how long do you need to wear these sensors? Potentially you could wear them for a week or two, and then you might be able to get enough data just from GPS after that. Sensors sense, and so we're developing sensors to measure very specific things. We might be measuring the wrong things. It could be the case that what we're sensing is a good proxy for something else, but this is a limitation of the method. And then, of course, these studies are all designed with the idea of using cheap sensors, and by that nature, they are cheap. And so there's issues with calibration and QA/QC. How do you deal with this? How do we incorporate data quality measures in our models? And then we've touched on this quite a bit this morning. Personal monitoring is quite personal, and so how do we deal with these issues? And then finally, real-time sensors are real-time. That's going to be a large amount of data. And I think another issue is that especially these exposure sensors measure, for example, at 50 hertz, and that might not be the time scale at which the body responds to exposures. So we might be measuring things at a very fine time scale, but the time scale of interest might be more, hours, minutes, kinds of time scales. And then a final issue that we touched on briefly is that we would like to have good patient engagement with this. So you would like to share data, but does this make a problem if we're trying to use this as an epidemiology tool? If people change their behavior, how does that affect the use of the tool? So thank you very much.